We may be missing some people today because the storms last night knocked out internet in some areas. So, a lot of storms this weekend. I know Oklahoma had like at least 7 tornadoes, and they're thinking it could have been 12 or 13. They're still trying to figure all that out. But no major injuries, no deaths. So they did well dealing with all that over there. But so hopefully your weekend went well. It was certainly going to continue to rain. So it was a wet weekend. Going to continue through today. Go get more rain. But I made it to a movie on Friday. Saw Here. That's the name of it. Here. And has Tom Hanks, Robin White. She's Buttercup from The Princess Bride. And a few other well-known folks. So, but yeah, Here is interesting. It's kind of artsy because it's named because they put one camera. They just set one camera up, and it recorded right here. So everything that happened here is what the movie's about. Because the camera never moves. That's the whole hour and 45 minutes or however long the movie is, 2 hours or whatever. You're just looking from one camera. It never switches. It never close up on anyone. Never changes. It's just looking right here. It has like even dinosaurs going through, asteroids hitting the earth and cleared up. This big colonial house back in the 1800s. You're looking down the driveway to that house and what's going on out in the yard. American Indians, before that house was built, time there was some Indian couple. And then you're looking in a living room in like the 1900s, looking out the window and seeing that colonial house across the street and old timey cars driving by and the people that live in the house. And fast forwards to even 2020, there's some scenes with the people who live in there just like currently and back in the 1990s, the couple. So you're always looking to the same camera here. So that's why they named it Here, because that's what you're looking at the entire movie, just here. And what all happened right here throughout all of history. And so it's weird. I liked it in the end. I thought it was pretty good, but some of it just seemed okay. They didn't even need that scene, or they put some scenes in there just to make a political statement or something, but it didn't add anything to the movie. But most of the movie was pretty good, just different. So, and I made a trip over to Oklahoma this weekend. I went to the Sooner game on Saturday over in Norman, Oklahoma. Took my son-in-law with me. Had a nice 12-hour trip. Time you drive there and back, catch the whole game. That was a good time. So, well, is this it? We're going to be missing 5 people today. I know some people have some internet issues with the storms, but hope everyone's dry and safe. Let's take a look at what we have this week. Yes, I did pick up a head cold, so I got the deep voice going here. All right, Algebra 3, let's look at our grade screen as usual. We scroll down. See, we are now done with Module 3. What was due over the weekend was the practice test and the test, parts 1 and 2. So hopefully you have completed everything and are ready to start Module 4 with us. This will take us all the way to the semester exam down here. So all the way to the semester exam. I think there's something else I got to have right in between there, but this will get us pretty much there. So we're going to do exponential functions this week. We'll do logarithmic and properties of logs next week. And then the week before Thanksgiving, solving exponential equations with unequal bases and graphing them. Then when we come back, we'll look at graphing log functions. And I think there's something else between that and the semester exam. But 4.01, one lesson this week. 4.01. Let's take a look. So, first 3 folders are closed. Now I've opened up folder 4. Let's take a look at what we're studying. Have you ever watched a ball thrown high in the air? Surely at some point. When the ball reaches its highest point, it kind of seems like it stops for just a moment, especially if you throw it straight up. There's a moment where it just stops before it starts falling down again. If you've not seen this, try it. At the top of the ball's flight, it's reached the point with like 0 vertical velocity because it goes slower and slower and slower until it stops and then starts going back down. It's its fall back to earth, and then it goes faster and faster until it stops, right? So it's changing exponentially. The speed of the ball is exponentially changing. So we're going to, after this lesson, there's to answer these questions. How is an exponential function created? How can the properties of exponents help solve exponential equations? And what are some real world applications? Page 2. So an exponential function is a function where the variable is located in the exponent, right? 3 raised to the x is an exponential equation. X to the third is not. That's just a cubic equation. That's not exponential. It's just a cubic function. So an exponential function has to have x as an exponent. So our little definition there. Function with variables located in the exponent, and the base is a real number. That's not 1. Because 1 raised to the x is not, that's actually linear. But here's some examples: 3 to the x, or 0.27 to the x power, or 4 to the x power minus 2, or 50 times 2 to the x power. Those are all exponential functions. So there may be times in your educational or professional career where you're faced with some numbers, some raw data. Your professor or your boss will say, "What do you make of this?" Well, your first instinct may be fold over the paper. Well, I can make an origami swan. No, don't do that. Don't do that. They're looking for you to create a function out of these numbers. Okay, example 1. So start off with some numbers. So like here's the x's 1, 2, 3, 4, and f of x, or the y, is 2, 4, 8, 16. So it's important to check the increments of the x. It should be increments of 1. That makes it easier to see what's going on. 1, 2, 3, 4. Now look how much the y's increase. So if we look at this, first it goes up 2, and then it goes up 4, and then it goes up 8. So this is not linear because it's not a constant change. So let's look at it differently. If we say 2, 4, 8, 16, actually it's going times 2 each time. It does go plus 2, plus 4, plus 8, but it is constant, and that is multiplying times 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this means that 2 is the base of our exponential function. This is f of x equals 2 to the x power. Because 2 to the first power is 2. 2 to the second power is 4. 2 to the third power, whatever the x is the exponent. 2 to the fourth power is 16. You can check that and make sure it works here. When x is 1, if it's 2 to the x, it would be 2 to the first power, 2. And that's what I was just going through. 2 to the third power is 8. 2 to the fourth power is 16. So it does work. This is f of x to the 2x equals 2x. Let's look at their second example. Let's look at these numbers. X equals 2, 3, and 4, 16, 64, 256. Definitely not a linear function. It goes up 48, then it goes up 192. But it is multiplying times 4 each time. 16 times 4 is 64. 64 times 4 is 256. And we can substitute those numbers into the function of f of x equals 4x, since it looks like it's 4x, since it's multiplying 4 each time. If it's 4 squared, it is 16. 4 to the third is 64. 4 to the fourth is 256. All right, let's move to the next page. Solving exponential equations. Okay, this is good. Let's start with the most basics. And I'm going to put it up so we have some examples for our notes. So the most basic, if we just said 3 to the x equals 3 to the fifth, it's like, okay, can we solve that? Well, sure, x would have to be 5, right? Because the only thing that's going to equal 3 to the fifth, oh, come on, lights. The only thing that's going to equal 3 to the fifth is 3 to the fifth. So x equals 5. It's not focusing well this morning either. All right, so if we had like 2 to the x equals 32, then we can say, okay, we need to solve this for x. Well, what is 32? 2 times 2 times 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So this equals 2 to the fifth, so x equals 5, because 2 to the fifth equals 32. So solving exponentials works it's very basic, pretty simply. So they look at that like here 3 to the x equals 3 to the fifth. So obviously the solution is x equals 5. They did 3 to the x equals 243. Well, 243 is 3 to the fifth power. So again, x equals 5, because they're taking 3 to the fifth and making it the actual number that it equals. Some exponential equations will have binomials in the exponent. So we'll have to look at our properties again that we've used before. Let's review these properties. The product property, the quotient property, the power of a power, and negative exponents. So it's important to remember these properties.
So your other work, you have 2 ed puzzles. There's one about the biomes and then the climatograms. Just to help it stick in your head, they are short. They're not 5 hours long. Your text is in here.
Exponential properties. Well, I didn't write that very well. Okay. Writing's not going well today. Sorry, guys. It's a day-by-day thing for me. Exponential properties. Okay. Product. Product property. If we have, and these properties work, doesn't matter. I'm going to do it with just x's for right now. X to the a, that looks like a 9. I got to write better. Times x to the b. If we have x to the a times x to the b, that's x to the a plus b. So let's do an example over here. X to the third times x to the fourth equals x to the 3 plus 4 equals x to the 7th power. So that's an example of the product property. If we have 2 exponentials with the same base, that's important, they both are x, then we can just add the exponents together. So x to the third times x to the fourth is 3 plus 4, x to the 7th. Okay, what are the others? Look at quotient. If we have x to the a divided by x to the b, that is x to the a minus b. Example again, if we have x to the 7th divided by x to the 5th, that is x to the 7 minus 5. It equals x squared. Because all we have to do is subtract the bottom exponent from the top exponent. Let's look at the power property. That says if we have x to the a being raised to the power of b, that's going to be the same as x to the ab. You multiply them together. So in our example over here, if we have x squared being raised to the 4th power, that's x to the 2 times 4. It's x to the 8th. All right, it's all looking familiar. And then the last thing we need to look at, if we have x to the negative 3rd power, let's just do it as a generic negative b power, just like negative b power. We can make it positive by moving it into the denominator. Or just the opposite. Let's just 2 examples. If we have x to the negative 3 power, that's the same as 1 over x third. If we have, let's say, 2 over x to the negative 4th power, 2 divided by x to the negative 4th power, that's the same as 2x to the 4th power. Really over 1, because there's nothing left down here when we move that to the top. If you put it over 1, that's the same as 2x to the fourth. So these are the properties we're going to be using when we deal with these exponential equations. So this is just a refresher. This is great to have in your notes. You may still have in your notes from earlier in the year when we've looked at some of this. But the product property, the quotient property, the power property, and dealing with negative exponents. How do you fix a negative exponent? You move it. If it's on the bottom already, like this one, you can move it above into the numerator. So, all right. So after that little review, let's see what problems they're going to throw at us today. Product quotient, and they're all right here. If you need to review those, you can click on that, and it gives you a little refresher, even with fractions. Page 4. Let's take an example of rewriting an exponential equation with equal bases. All right, this is a good review. We need to understand how to do this here.
First, create equal bases. Before solving for the variable, the bases of each exponential expression in the equation must be identical. Rewrite the numbers 256 and 16 with a base of 4 and exponents 4 and 2, respectively. According to the properties of exponents, when the denominator of a fraction contains an exponent, such as 1 over 4 to the fourth power, you can rewrite the expression with a negative exponent. On the right side of the equal sign, there is a power raised to a power. By the power of a power property, these exponents will be multiplied. Be sure to distribute Now, solve for the variable. Once the bases are identical, eliminate both bases and find the value of the variable. Now, check your work. Substitute the value of the variable into the original equation to confirm the solution. The solution x equals 7 is correct.
So I would have solved this a little differently. They started with 1 over 256 equals 16 to the x minus 9. And I looked at it and I said, well, 256 is 16 squared. So I would leave it base 16. Now, 16 squared, we have to write it above the numerator as a negative, because that's the same thing as 16 to the negative 2 power. But the important thing about solving exponential equations is you have to have the same base. These are both base 16. Now, they went ahead and converted them both to base 4, but then you have to change this one as well as this one. But if you have the same base, once you get to that point, you can just take the exponents and set them equal to each other, because they're both base 16. So the exponents have to be the same. This has to be negative 2 in order for these to be equal. So if we just drop those, once we get them equal to each other, drop those, we just solve this. And so we add 9 to both sides. So 7 equals x. X equals 7. We get there quicker than they did because they went to 4 squared raised to the power of x minus 9, which is fine. You can do that. If you don't recognize that these are the both base 16, you can do it the way they did it. So let's go over the basics of solving those again. If you have, let's do something like 2 to the x equals 8 raised to the power of x plus 1. I don't even know if this solves nicely. I just made it up. We can't set x equal to x plus 1 because these are not the same bases. This is a 2 and this is an 8. But we can make them both the same because 8 is a power of 2. So this would be 2 to the x equals 8 is 2 to the third power, right? 2 times 2 times 2 is 8. So if we change 8 to that and then take it to the power of x plus 1, now these have the same basis. But we have to simplify this. We got to go back to this rule, the power to a power. I got a power being raised to a power, which means I multiply. So I have to multiply this. So this is 2 to the x equals 2 to the 3 times x plus 1 is 3x plus 3. Now the bases are the same. So I can drop those and say x equals 3x plus 3, subtract 2x, 3x, I'm sorry, subtract 3x. So this is negative 2x equals 3. So x equals negative 3 halves. So it works. It's just a fraction exponent. So 2 to the 3 negative 3 halves power would equal 8 to the negative 3 halves plus 1 be negative 1 half power because you're adding 1 on there. But that's how you can solve that. You're just trying to get the exact same base. So once you get the same base, you can drop it. And that's just based off the principle that if I say 3 to the x equals 3 to the 7th, the only possible solution is x equals 7. Because these are the same base, you drop it, x equals 7. That's the only way that 3 to the x could equal 3 to the 7th is if these are the same number. I mean, you can try it. No other number is going to work. If x equals 6, does 3 to the 6 equal 3 to the 7th? No, 3 to the 6 is not going to equal 3 to the 7th. Not. The only thing that'd be equal is they both have to be 3 to the 7th, right? That just makes sense. So when we have two different exponents, they have to be equal to each other. That's the only way this can be equal. They both have to be equal to each other. But we can only do that after we get them to be the same. These were not the same base until we rewrite that. We rewrite that to make it the same base. All right. Let's see where we go from here in our problems. Example 2. Solve this exponential equation with a square root. Ooh, boy, they're giving us a good one here. So let me write this down. So we want to rewrite this and this to get them both in the same base. Well, 121 is 11 squared. We can recognize that. So on the right side, we'd have 11 squared. That's what 121 changes into. And it's being raised to the power of x plus 1. So that's a power to a power. On this side, if we say 11, the square root of 11, going back to our exponential to logarithm, we can rewrite that as an exponent. This square root, remember, would be the same thing as a 2 outside. And the inside, we just have an 11 to the first power. So that's the same thing as 11 to the 1 half. Because that's when they don't put anything, it's assumed to be a 2. And when it's just an 11, it's 11 to the first. So this is 11 to the 1 half power being raised to the power of 12x. So now we've got base 11 on both sides. So let's simplify. 1 half times 12x. This is 11 to the 6x power. Over here, we've got 11, 2 times x plus 1. This is 11 to the 2x plus 2 power. Same base. It's simplified. We can just set the exponents equal to each other. 6x equals 2x plus 2. Just the exponents. Subtract 2x. So 4x equals 2. X equals 1 half, because that's what 2/4 simplifies to. X equals 1 half. And then they test that. So they said, okay, so what would this be? square root of 11 and 1/2 raised to the power of 12 times 1/2. So that would be the square root of 11 raised to the power of 6, because 12 times 1/2. On the other side would be 121 raised to the power of 1/2 plus 1. That's 121 to the 3/2 power. So it's like, okay, so how do I do this? Well, we can rewrite those both as power of 11 again. This is 11 to the 1/2 to the 6th. This is 11 squared to the 3/2. Multiply 1/2 times 6. This is 11 to the 3rd power. Over here, if you have 11, 2 times 3/2, this is 2 over 1. When you multiply, you just multiply straight across. This is 6 over 2, which simplifies to 3. It's 11 to the 3rd, 11 to the 3rd. Because 2 times 3/2 would be 6/2. 6/2, 6 over 2 divides to be just 3. So when we check it, this is the correct answer. Because when we simplify everything, they do equal one another. Okay, let's see what page 5 holds for us. Applications. So to suppose you were to find a bottle with a genie inside, it can grant you one of 2 wishes. Here's your 2 choices. You can either receive $100 every day for the next 30 days. So for the whole month of November, the genie says, I'll give you $100 every day in November. Or on November 1st, I'll give you a penny. And on November 2nd, I'll give you 2 pennies. And I'll give you double the amount every day for the November. So on the 3rd, you get 4 pennies. And on the 5th, you get 8 pennies. And on the 6th, you get 16 pennies. Which one would you choose? I'll let you put that in the chat. Think about that. Do you want $100 or do you want a penny? Now remember, the penny is going to double every day. $100 is going to be the same every day. So today is the 4th. By now, you'd have $400 because you got $100 on the 1st, the 2nd, the 3rd, the 4th. You're at $400. With the penny, let's see what would you have so far. You have a penny on the 1st. You'd have 2 pennies on this. So I give you 3 pennies by the 2nd. And then you get 4 more pennies. You'd be up to 7 pennies. And then today you would have got, 8 pennies? So you'd have 15 cents today. But you'd have $400 on the $100 every day. But this is going to continue all the way to the end of November. Now, Jonathan says, oh, that's easy. I'll take the penny. Give me the penny. I'll set it with my 15 cents. Well, you got your $400. He said, I'll be okay. By Black Friday, I'll have enough to get what I want. Madison's going with the penny. Anybody else going to choose? You want $100 every day? Shay, take $100 every day. She says, I want the $400. See, Black Friday is on the 29th this month. So by the 29th, Shay's going to have $2,900 to spend on Black Friday. Jonathan says, I've seen this before. It's a crazy number. Exponentially. Let's see what we had. The Black Friday's on the 29th this year. So $100 every day. Yeah, we'd have $3,000 by the end of the month because on the 29th, we'd have $2,900. With a penny, let's see, by the 29th, you'd get $2,684,000 just for that one day. On the 28th, you got $1,000,003 on the day. So altogether, if you add the whole month up, you'll end up with over $10 million by November 30th. So when you see that genie, tell him you're happy with the penny as long as he doubles it every day for the month. Because exponentially, it may start slow, but if you remember how an exponential graph goes, it gets crazy. How quickly it goes up. Let's look at an exponential graph of a penny. Y equals 0.01 to the power of x. Oh, I guess I should make that go the other way. Let's see, is it No, wait. There we go. Yeah, +1 plus. I got to get it. No. I got to get it to where it's going to put it at 0 on there.
I don't know if you remember, but orbit notes people usually only use that.
Okay. Yep. Starting out on the first day, there's a penny. On the second day, it goes up really quickly. You see how it starts slow. The first calculations stay way down here, but when it starts going up, it goes up incredibly fast. Goes up incredibly fast. See, it's just starting at pennies, dollar, $2, $5, $10, $20, but then it starts going up. Wait a minute, doubling up: 1,000, 2,600, 5,200, 10,000, 20,000, 40,000, 80,000, 167,000, 671,000. To where the last day of November, you're getting $5 million. It's just insane how exponential can grow so fast the farther it goes. So, exponential growth function. Let's talk about an exponential growth function because this is used a lot in science, in looking at how bacteria grows. Like some bacteria may double every 3 days or something. And as it doubles, the first few days, you don't have much bacteria, but a couple of weeks in, your bacteria is growing. If all the bacteria is doubling, it goes really nuts. So that's an exponential growth function where the initial amount grows significantly as time passes. Doubling the amount of money in your pocket each day for 30 days is the example. Here it is. I was using the wrong function in Desmos. 0.01 times 2 to the t. Yeah, I forgot the 2 in there that you're doubling it. 0.01 times 2 to the t, where t is the time. How many days? You start with a penny, and then the rate of growth and the time, the x. So substitute 30 in there, and that's where you get the total. The total for 30 days is $10,700,418.24. So a basic exponential growth function. Let's look at exponential growth.
All right, guys, go ahead. If you got, let me see.
F of x equals a times b raised to a power, where a is initial amount. That's how much you start with. The a is what you start with. B is the rate of growth. And x is the time. And that can be defined in days or months or whatever. Years, hours, depends on how fast this rate is. Is this rate it's doubling every hour, then x would be the number of hours. Is it tripling every 3 days, then x is how many groups of 3 days do we have? So initial amount, rate of growth, time. So the penny we were looking at would have been a penny that doubles every day. 0.01, 2 to the x. So let's look at the graph of the function. Oh, okay. Now they want to do the graph of that. So we'll pull up Desmos and I'll put the correct formula this time. Equals 0.01 and it times 2 to the x. See, by day 5, we're still down here at like 32 cents on day 5. Day 6, we're at 64 cents. But by day 10, we've made it. Oh, I can't get to right. Where's the 10th? Oh, sorry. $10.24 is what we've collected total. This is the total. But you see, after that, it starts going up really quick. So by day 20, we're way up here. Wow, 20 is this line here. So I'm trying to get to how much money we have by day 20. It's way, way up there. It's going a lot higher. We're not to 20 yet. We're at $5,000 and we're not to day 19 yet. So yeah, exponentially it starts going just absolutely crazy. If you zoom out, it's just really nuts. So all right. The base of an exponential growth function will always be greater than 1 since the amount increases as time passes. It'll just keep going up. Let's see. There's many applications of exponential growth. One can be found when computing compound interest in banking. Interest is money that a financial institution like a bank contributes to an account based on the amount of money in the account. Most accounts earn simple interest, so based on principal. But the principal is the amount of money deposited by the individual. Compound interest is interest that's not only giving you interest on the principal, but also on the interest you got last month. See, that's where it's nice to invest. That's why investing is so important. Because, so here's the thing. So if you're 21 years old and you start a 401k retirement account, let's say it's a Roth account for when you turn 65, you want to retire. So you put money in at 21. So let's say you put $1,000 in this year. Boom, at age 21. Well, if you didn't put anything else in it, but it earns, let's say it makes 8% interest. So it's going to earn $80. So next year's going to come around and now you've got $1,080. So you're going to get another 8%. We're going to say, let's just say it averages 8% a year, which means some years it's really good and some years it's really bad. But over the whole time, it averages 8%. If we got 8% every year, that means next year you're not going to get $80. You're going to get $80 plus another 8% on the 80 interest it earned this year, because that's still in the account. So next year it's going to be $1,080 getting 8% interest. So you're going to get like $86.40 because you'll get 8% of the $80. And then the next year you'll get interest on that interest. And so the interest over time starts getting bigger and bigger and bigger, because at some point now you've got $2,000 in there because this interest adds up. Because you had $80 and then you got another $86.40, which means you got another $164 and $166.40. So you're getting interest on $166.40, and then the next year you're getting interest on that interest and interest on that interest, or by the time you retire, let's take a look at that and see if we could kind of estimate how much you'd have retired if you made 8% every year. We can come up with a formula for that. So let's say if we started with $1,000 and it makes 0.08, it makes 8% interest per year. Why is it going down? Did I do something wrong? We just had the formula on there. Rate of growth. Oh, well, yeah, I got to put 1.08 because I still have my original money. I still have the 1,000, but I'm adding 8%. So it's 1.08 every year. So we got to zoom way out because we started way up. We start at 1,000. See, on day 0, we've got $1,000. Right, we got $1,000 on day 0 because that's what we start with. Now let's go to, let's say 40 years from now. Let's go to 40 and see what it equals at 40, because that $1,000 is going to grow and grow.
There you are. Okay.
40 years. Looks like I got $21,000. In 40 years, you'd have $21,000 without putting another dime in it. $21,724.52. If you made 8% every year and just left it in there for 40 years. $1,000 becomes $21,000 because you're getting interest on top of the interest. But hopefully, you're going to add another $1,000 next year and another $1,000 the next year and another $1,000 a year. So this will actually turn into millions of dollars by the time you're 65, because every year you're putting $1,000 in there. But if you've never put another dollar in there, you'd still have $21,000 in 40 years when you're retired. But think, if you keep putting $1,000 every year and that gets interest and that gets interest and that gets interest, you'd have millions by just putting in a small amount early. But the important part is You start young. You don't wait till you're 45 to start putting away for retirement because it'll take you a lot longer. So here is a formula for money. Here we go. Let's write this one down. This is the one you would use to calculate anything dealing with money. Total amount. This is how much you'd end up with. Total amount. Starting principal. That's the amount you started with, right? This is the $1,000 I put in my account. One plus, because you keep that $1,000. That's why you have the one plus. And this is our rate of interest as a decimal. So 8% is the same thing as 0.08 as a decimal, for example, rate of interest. In number of times per year interest is received. The number of times per year the interest is received. Right? Do they give it to you monthly? Do they give it to you quarterly, which is 4 times a year? Do they give it to you just once a year? And then T equals years. We got this T up here, N times T. Okay, so let's look at, for example, I was looking at that 8% per year, but if they gave us the interest monthly, amount equals $1,000. 1 plus, we're going to say we're going to make 8%, but they're going to give it to us every month. And we're going to check to see in 40 years. So 12 times 40. Because they give it to us 12 times. They don't just give it to us once a year. You actually make more money if they give it to you every month, because that means on month 2, you're getting interest on the interest you made in month 1 instead of waiting until the end of the year and getting $80. So let's just see what that's going to equal with our calculator. All right, I guess I'm just going to make it a little smaller, see if I can help get it on the page. 1,000 times, parentheses, 1 plus, parentheses, 0.08 divided by 12. That's not 12. 12 raised to the power of, parentheses, 12 times 40. What's that going to equal? 24,000. See, we figured $21,000 with just getting interest once a year. Once a year, at the end of the year, they give me $80. But if they give it to me every month, they give me a little bit of that 8% every month. It'll actually end up $24,000. And that's how your retirement accounts work, really, because it's calculated all the time. You can get interest on your interest in your accounts like that. So $1,000 turned into $24,273.38. Let's see what we made after 1 year, where it would have been just $80 with simple interest. Right, 1 year, simple. If we just made 8% at 8% would be $80. Okay, 1 year simple interest at 8% would be $80 on 1,000. But let's use this formula where let's say we get it every month, and this 40 will just be 1, just 1. So A equals 1,000 times 1 plus 0.08 divided by 12. 12 times 1. So let's say with the compound interest, we're getting it every month. Let's see what that equals. First, let's simplify some things. What's 0.08 divided by 12? That's 0.06667. So this is actually 1.06666. That's what that is. And this is just 12. So we'll simplify our calculations to where this is just 1 point. Oh, there's another zero in there. Two zeros. 0, 0. So that'll simplify. Let's say 1,000 times parentheses 1.00, and then I'll put a bunch of sixes. Try to get it accurate as I can. Raised to the power of 12. So we'd have 1,082.99. So we would end up with 82.99.9. We'd end up with $83. If it's calculated every month, we end up with an extra $3 just because we're getting interest on top of the interest each month. So in month 2, I'm getting interest on my $1,000 plus interest on the money I made in month 1. And in month 3, I'm getting interest on the $1,000 plus the interest on the money I made in months 1 and months 2. So it just builds up nicely. So this is a formula. Let's do it. This is the formula you should have in your notes for compound interest. Compound interest. Because you'll need that in assignments on compound interest. All right, let's go back and look here. Let's see. If $100 is invested at 5% per year, compounded quarterly, so that's every 3 months they give you interest. What's it worth at the end of 2 years? So here's a video. 2 minutes. We'll go ahead and watch this video.
If $100 is invested at an interest rate of 5% per year, compounded quarterly, how much will the investment be worth at the end of 2 years? To answer this question, first use the scenario to define each variable. The principal, P, is $100. The interest rate on the account is 5%, which is written as the decimal 5/100ths. The account is compounded quarterly, which means 4 times each year. Therefore, N is 4. The question asks you to find the account value after 2 years. So, T equals 2. Now that only one variable is left, use the order of operations to solve for that variable. When working with money, round the solution to the nearest cent, or nearest hundredths. So, after 2 years at a 5% interest rate, compounded quarterly, the initial $100 investment will be worth about $110.45.
So as this account is compounded more and more frequently, if it was monthly or weekly or daily or hourly, the amount in the account would not change as significantly and eventually may not change at all. But when the principal and frequency of the compound increases, the amount earned does increase. So check it out. So it said if it was monthly instead of quarterly, it'd be 110.49 cents. If it was weekly, it'd be 51 cents. You only get a couple of cents between monthly and weekly. And daily, you'd gain another penny. So when interest on account is compounded continuously, which would be unheard of, there's a growth function called this. I'm going to put this in our notes too, because there are times you use this. Here's a second growth formula. So this was our exponential growth. Oh wait, and there's our compound interest growth formula. All right, but there's also this one. This is continuously. And you're like, when would you ever get interest continuously? All right. Wow. Well, you wouldn't money. This really doesn't apply to money. This is used in science. Like if we have some bacteria that is growing and it's increasing at a rate of 10% per day or something, the amount of bacteria, that's happening continuously. every second that bacteria is growing. And so this is used a lot in science. A equals PERT. And you're like, wait a minute, where's the numbers? E is a number. In math, E is a number. It's even on our calculator. Right there. See E? Let me clear everything. See that button E? If I click E and you want to know what E equals, E is 2.718281828459045. And it goes on and on. It's kind of like pi. You know, pi is a number, E is a number, I is a number. You know, that's a square root of -1. It's an imaginary number. But E is actually a number. So this is actually P times 2.7182818 ... raised to the power of the rate times time times years. So E is actually a number. So don't get confused on, wait a minute, what am I doing there? E is a number, and it's on your calculators. So, all right, let's close it out. So A equals PERT. So in this function, A, P, and R all have the same meanings. A is the amount you have after T years. P is the starting amount, the principal. And the interest rate is the R. But notice the variable N is no longer needed because it's not being compounded weekly or quarterly or whatever. It's being compounded continuously. Continuously. Then we got that other letter exists in this place, E, right there. E is not a variable, it's a constant. It's equal to 2.71828. We just saw it in the calculator. It's used in a bunch of science and mathematic applications, which is why it's given a letter. And you'll see E to the X and stuff like that. So if $500 invested in an account that's 6% per year, that's compounded continuously after 3 years using the E, so you'll never find a place that'll give you continuous interest, but PERT. So we got $500. The R is going to be 6%, 0.06, and T is going to be 3 years, so times 3. So if we punch that in, 6 times the point times the 3 years is 0.18. Then E to the power of 0.18 is 1.192717, and multiplied times the 500 gives $598 after 3 years. Round it off to the nearest penny, and you get 598.61 cents after 3 years. If it was compounding continuously, which no one would do that because it's crazy calculations. And you know, how could you ever get a bank statement? Because anytime you get a bank statement, it would already be expired because another second has passed. So, more on exponential growth function. There we go. Let's see. The population of a small Midwestern town can be found by using this function, LERT, where P is the population. If we want to know what the population is, after T years, and L represents the initial population. So I said, this is how many people first started this town at whatever year we're looking at. So like they said, in 2009, there were 50 people living there. And it grows 10% per year. And that's kind of a continuous growth. How many people would be in 2020? So 11 years later. So it's like, okay, let's take the LERT. We put 10% growth in for the rate, 0.1. 50 is the initial population. And then we want to know after 11 years, because 2009 to 2020 is 11 years. Work the math, and there should be 150 people. So the population will about triple because we started with 50 people. And since it's 0.2, it's point anything, we're going to round down because you can't have point anything of a person. We got 150 people because populations are whole numbers. We don't use any decimal. We got half a person living there. Ooh. So it says round it to the nearest whole number. Here's a science thing with a bacteria. Has 10 bacteria when they started the experiment, and it triples every day. So after a week, how much bacteria do we have? So we're going to write our function. Let's see, bacteria. Looking for BT. The initial amount is the L, the 50. The growth factor would be B, and T is the time. So they went 10 times 3 to the t, which was going to be 7 because they want to know after 1 week. So 10 times 3 to the 7th, find the number of bacteria after 1 week, is 21,870. So 3 to the 7th is 2187 times 10. So that 10 bacteria they started with is going to be 21,000, over 21,000 after a week, because it's tripling every day. Every day, get 3. Every one of those 10 turn into 3 more every day. So it'll be 30 at the end of the first day. Okay, our last page of the lesson. Let's look at exponential decay. That's the other thing that can happen. The base of all exponential functions must be a positive real number, not equal to 1. So an exponential decay function would be smaller than 1, right? We don't have a full 1 left at the end of the day. We have less than 1. So one example of an exponential decay, let's write this down. Starting value or amount is the L. R is the rate of decay. And of course, time, being however you define the time based on the rate. Is it decaying every day, every month, every year? What is the rate of decay? That'll determine what this unit is for the time. So they're looking at an example here with like a value of a car. Okay, value of a car. So this is a good example. And cars, so it says you're going to buy a car for $15,000, which would be that must be a used car. And it decays, the value goes down 20% per year. So yeah, it must be a used car, because new cars go down faster. You lose more value more quickly. So it says after 5 years, how much is your car worth? And this is a good example of decay, because cars go down in value. The longer you own the car, the less it's worth, until it gets old enough to be an antique. But that's a long time down the road there. So let's look at this formula to see what our $15,000 car is going to be worth in 5 years. So the amount in 5 years will be the 15,000 starting 20%. So 1 minus 0.20. Now 1 minus 0.20 is 0.8, right? 5 is our years. Now, think about this. 5. Why would it be 0.8? Well, if we lost 20% of the value, this is the number on how much we've kept. We still have 80% of what the car was worth after a year, right? We've lost 20% of the value, so that's gone. We subtracted 20% of the value. We still have 0.8. So when you see this number, if you just saw, we didn't see anything but just this, we should know, oh, this is a decay formula. It's going down because this is less than 1. If we just multiplied it by 1, it'd keep the same amount, right? If we started 15,000 and 1 to the 5th power is still 1, we'd still be worth 15,000. So anytime this is less than 1, less than 1.0, it's decay. It's losing, it's shrinking, it's getting smaller, it's decaying, it's going away. Anytime that this number in our parentheses being raised to a power is less than 1. All right, let's get our calculator and see how much our car is worth after 5 years now. Okay, this car that we love so much, and we shaved up $15,000, and if we financed it, we paid probably $19,000 or $20,000 because you had to pay all that interest. But let's see, 15,000 times parentheses 0.8 parentheses raised to the power of 5. Our car is now worth $4,915.20. So you lost $10,000 in value in the car, and that's probably pretty accurate. If you buy a $15,000 car, it's probably worth about $5,000 in 10 years because cars go down in value. So if you buy a $60,000 car, it's going to go down a lot faster, and in 5 years, it's probably going to be worth 12, maybe 15. It's going to lose a whole bunch of its value. This lost 2/3 of its value. Probably lose 3/4 in a new car. Whole thing, something like that. It loses a lot of money. But here's where they calculated the same thing. Found out $4,915. So after 5 years at a 20% rate of depreciation, that's all it's worth. What do they have here? Example 2. Take a look at the graph of this function. X represents time, while the Y is the value of the car. So it started at $15,000, and over time, the value is going down, 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 down to at 5 years, it's at the $4,900. That restricts it to 5 years. If we took off the restriction, we'll look at 10 years, it's worth less than $2,000 because that's how the value of the car. It never gets down to zero. The car's not worth zero. If nothing else, it's scrap metal that you can get $100 for. So but it'll just get closer and closer and closer to zero as time goes on. And if you keep it in good shape, it may start going back in value when it gets really old, and if it's a good car. But anyway. When the decay of a substance or object takes place continuously over time, then you use E. Exponential decay, the LERT. So this is used a lot in medicine, where the rate could be a negative amount. So remember, negative exponents turn the base into a fraction. So if we have 250 milligram dose, so they do use these formulas a lot in medicine to figure out how much medicine is left in your body after so many hours. So we substitute 250 for the L. And it says the question asks for the amount of medicine in the bloodstream after 8 hours. So if it's decaying at a rate of 5% per hour, so that's a negative 0.05 times 8. So it 0.4, negative 0.4 after 8 hours. So when they put that in the calculator, 250 times E raised to the power of negative 0.04, 0.4, they should have about 167 milligrams of this medicine left in their bloodstream. If you calculate this and you get a number bigger than 250, you did something wrong. Like they're not going to have more in their bloodstream. If you know this is one of those questions asking about the decay, and anytime it tells you the rate is going down, it says leaves the bloodstream at 5% per hour. Maybe you didn't make this a negative. You put 5 as a positive, 0.05. And you end up with like, hey, look, now they've got like 400 in their bloodstream. No, they're not going to think about your answer. Look at your answer and say, does that make sense? Why would they have more in their bloodstream after 8 hours? You did something wrong. Here's another one example. 200 players in a golf tournament, and a quarter of the players are eliminated after each round. So after 3 rounds, how many's left? Well, it's not you've eliminated 3/4 because you only eliminate a quarter of what's left. So it's 1 minus a quarter. So you have 3/4 left because the rate of decay is 1/4. So you start with 200 and you got 3/4 left every round. So you'll have 84 players left after 3 rounds of the 200. All right, lesson summary right here. Exponential equations. Remember, we got to make the bases equal on both sides. Solve for the variable after you eliminate the identical bases. Exponential growth for compound interest right here. A equals P 1 plus Rn over NT. Continuous is A equals PERT. And decay is going to be a negative R. Decay is a negative R. So you're going to be subtracting it from 1, basically. Okay, practice problems. Let's look at the assignment. What exponential function represents the data? Oh, so how much is it being multiplied each time? Is this x to the fourth? Is it 4 to the x? Is it x to the fourth minus 17? Is it 4 to the x plus 17? Solve this one. Make them both the same base. Right now you got a base of 3 and a base of 9. Here you got a base of 64 and a base of 16. You'll have to convert both bases. You can make both of those base 4. So don't forget our power to a power property. You can make both these base 5. This is base 5. This is 1 over 5 to the negative 2 power. Here's a square root one, but you can rewrite that as a power of 7. 7 to the 1/2 is the same as the square root of 7. You can write 49 as base 7. $360 invested, 4% per year, compounded quarterly for 18 years. How much money? Now, here's one of those things, too. If you calculate and you say 175, how did you lose money if you're getting 4% per year? So you should be able to eliminate that answer immediately because that's less than what you started with. That doesn't make any sense. Here's one that starts at 535 and makes 6% per year, compounded continuously. There's that PERT. 10 years. How much is that going to be worth? Continuous. Bacteria culture begins with 4 bacteria. It doubles every hour. How many you have after 8 hours? Again, that's the EP because it's continuous. A jet ski depreciates. Okay, value's going down 11% per year. If it was $8,000, how much is it worth after 5 years? And it's not going to be $13,000. Again, it's not going up unless you made a mistake. And here's one of those medicine questions. They start with 50 milligrams of medicine, leaves the bloodstream at 10% per hour. How much will remain after 6 hours? And they give you the formula right there. How much will remain? So, all right. Most of those have a dummy answer that you can just throw out immediately and say, well, it can't be that. Okay, guys, we're going to be dealing with exponentials, obviously, this unit. So this was what we'll do the rest of the semester is looking at all these type of problems. So get in there and get familiar with it. Try the practice problems that's in the lesson. Work these problems on paper so you can get a good feel for it. The only way to learn math is to do math. I know you're watching math, but you don't really learn it until you do it. So do some math. You got about 15, 20 minutes left before the next class. So if you want to get started, you may be able to get these 10 questions done by then. So, all right, guys, that's all I got for you. That's why I only had one lesson. It was a pretty long lesson, but starting something new. So, okay, we will see you next time. Have a great week. This is a B day on Friday. So we only have class again on Wednesday for those of you who need to come or want to come.